All right, so for this lesson, we're going to do more with inequality proofs. You already know the addition postulate of equality, and that's basically where we talked about how equals being added to equals are still equal. You use that a lot in some of those triangle proofs. But now what we're going to do is talk about the addition postulate of inequality, and you're going to start getting a new reason for these proofs. And this is going to be equals added to unequals are still unequal, basically in that order. So really what you're going to be doing is probably writing this part. Equals added to unequals are unequal. And what that means basically, if you know that A is more than B, but C and D are the same, then if I add C to A and I add D to B, then I'm still going to have the fact that A plus C is more than B plus D. For example, take a look at this next piece. If 5 is greater than 4, and 3 equals 3. Well, by adding 3 to both sides of the equation, then 5 plus 3 is still going to be more than 4 plus 3. So the fact that we started out with an inequality and we added equals to that inequality, they remained unequal, but still in that same order then. 5 more than 4 is still going to be 5 plus 3 more than 4 plus 3. So equals added to unequals are still unequal in that order. Subtraction postulate of equality. We did this about segment subtraction and angle subtraction. Equals subtracted from equals are still equal. Well, now all we're going to do is we're going to say if we take away equals from unequals, they're still going to be unequal in that order. So take a look what's happening now. 5 is more than 4 and 3 is the same as 3. Well, if I take my equals and subtract them from my unequals, 5 minus 3 and 4 minus 3, we're still going to have 5 minus 3 being more than 4 minus 3. Okay, so make sure you understand that. I've got my equals here, and I'm subtracting them from my unequals. Where I was greater than to begin with, I'm still greater than to end with. So equals subtracted from unequals are still unequal in that same order. So these are some theorems that you will need to know then for proofs. Segment addition and subtraction. Okay, so segment addition and subtraction, substitution of inequality, a part is less than its whole, or a whole is greater than any of its parts. We didn't really talk about a part less than a whole. We always talked about a whole greater than a part, but it works both ways. In a triangle, the side opposite the larger angle is greater than the side opposite the smaller angle. But again, we have to be just in a triangle, in one triangle. We have this one that we just talked about now with we have unequals being added to or subtracted from unequals are still unequal. And then we've got this next one that's basically saying equals added or subtracted from unequals are still unequal. And then we also know this one from before that an exterior angle of a triangle is greater than either of its non-adjacent interiors. And then we've got the transitive inequality. So these are some new theorems that you need to know. The old theorems that you already have learned are still in effect. So I believe we're going to try a couple of proofs. Excuse me. So for this first one, they're telling you that B, C, D, and D all lie on the same line, AE. And they're also telling you that BD is greater than AC. I'm sorry, the BD is equal to AC. So if we kind of throw in some number here, from B to D, let's say we're going to call that 8. And then let's call from A to C. We'll call that also 8. All right, because it's congruent. It's telling you that. Well, somehow we have to prove that AC is less than BE. Okay, and I think that should be pretty obvious because AC is this thing that's 8. Well, BE is going from BC, CD, all the way through to E. So I think it should make sense, but the question is how do you write it up? So let's see what we can do. So we've got our statements and our reasons. And then we've got the fact that B, C, and D lie on line AE. B, C, and D lie on AE. And then we also have B, D, and AC are congruent. So this is given. Well, the next thing we can do is we can do some segment addition, because to get all of BE, we need to be able to add a couple of segments together. So if we do this, we can say that BE, that whole line segment, is equal to BD, what they gave us, and DE. And this is just going to be segment addition, or whole is equal to the sum of its parts. Either one, but I think segment addition probably is what you're going to be used to. So segment addition. Now we know that BD must be less than BE. So if you look at that thing, BD is going to be less than BE, because if you look at line 2, it's true that a part is less than its whole. So the only reason I'm keeping it less than is because the proof is less than. So a part is less than its whole. And then what we can do is deal with some substitution, because if we take a look at what we have been given in this first line, if we know that BD is congruent, right? If we know BD is congruent to AC and BD is less than BE, then we should be able to substitute in AC being less than BE. And again, we just kind of said this, it's substitution inequality. We've got an inequality and an equality, so we can substitute. So make sure that that works for you. So we've got some segment addition. We've got a part being less than its whole. We could have said a whole is greater than its part, but then it would have switched the inequality symbol. All right, let's try another one. So we've got two different triangles here. We know that E is greater than A, and we know that C is greater than D. But we've got to get to a line segment of AD, which is actually two parts, is more than EC, which is another two parts. When I say two parts, I mean that there's two segments of different triangles. So if we take a look at what we know for sure, let's start with this first one. Hold on. So statement reason. Statement reason. So we've got angle E is more than angle A, and we've got angle C is more than angle D. So these are all given. Well, if we separate this into different triangles, and you know what I'm going to actually do? I'm going to do something a little bit different. I'm going to do one given at a time, so this should be okay. If we just do angle E is more than angle A, in that particular triangle that we're dealing with, where E and A are a part of, this might make it more clear, then we know that the side opposite angle E would be line segment AB, and the side opposite angle A would be line segment EB. So we know for sure that AB is more than EB. And the reason for that is in a triangle, the largest side, or the longest side, however you want to write it, is opposite the largest angle. And then that's going to happen when we get to the next ones. So if we talk about the third given, or the second given, sorry, which is C is more than D, which is given, then in that particular triangle, and I'm going to run out of some room, but in that particular triangle, right, we can do the same idea. So angle C, line segment BD is opposite it, so then BD is going to be greater than an angle D, you're looking at BC, and that's going to be in a triangle, the longest side opposite the largest angle. Okay, so we've got that stuff going on. Well, we can deal with some segment addition here. We know that the yellow and the green and the yellow and the green can be added together to give you the whole piece. So here's where we're going to lose a picture for just a second. I'm going to come down here. So the next thing that we could say for 5, and we could definitely combine 1, 2, 3, and 4, but we could say that AB plus BD is going to be equal to AD, and we could say that EB plus BC is equal to EC. And the reason for this is going to be segment addition. Okay. Then the next step is going to be basically saying, well, we've already dealt with these individual parts, and we already know that AB from the top is greater than EB. And we also know that BD is greater than BC. So if we start adding these things, knowing they aren't equal already, we can say for this next step, get some more room. This is a problem doing this on the smartboard. Okay. 6. So we can say now this, that AB plus BD is greater than EB plus BC. And that reason would be unequals added to unequals are unequal in that order. So the fact by adding the larger pieces together has to be more than the smaller pieces. And then last but not least, I know already that this piece can get substituted in for those two parts. That whole can get substituted in for those two parts. And then finally, AD must be more than EC because of substitution inequality. So take a look at that for a second. Whoopsie, I don't know how this came up. Okay. So we've got, that's okay. So we've got angle E is greater than angle A, which gave us AB is more than EB. And then we've got C is more than D, which gave us BD is more than BC. So then what we're doing is we're taking the bigger pieces. I'm taking AB, which is the bigger piece. I'm adding it to BD, which is the bigger piece. And that's what's happening here. And then I'm saying it's more than the smaller piece added to the smaller piece. And then segment addition and substitution. Okay. Let's try this last one. So we've got TR and LR are perpendicular, which should basically tell you that these two angles down here, 2 and 3, are right. And we want to know that TL is greater than TR. So TL acts as a hypotenuse, TR acts as a leg. All right, so let's see what we can do here. So 1, TR is greater than LR, given. Then we can say angle 2 is congruent to angle 3 because perpendicular lines form congruent right angles. And then we can talk about the exterior angle being greater than, because we need to get inside the triangle. So angle 3 has to be greater than angle 1 because an exterior angle always has to be greater than a non-adjacent interior. So angle 3 is more than angle 1. And that's going to be an exterior angle of a triangle. Whoopsie, don't need that comma. Is greater than a non-adjacent interior angle. And then we can do some substitution here because we've got an equal piece here. We've got an equal, we've got an inequality, and then we can go by substitution and we can say, well, if 2 is the same as 3, but 3 is more than 1, then we have to say 2 must be more than 1. So angle 2 is greater than angle 1, and that's substitution inequality. And the fact that 2 is greater than 1, and we are in a triangle, then the side opposite angle 2 is the TR. So, I'm sorry, TL. So the side opposite angle 2 is TL, sorry about that. And it's greater than the side opposite angle 1, which is TR. And that's our proof statement. And the reason is going to be in a triangle, the side opposite the longer angle is the longest side. The longest side is opposite the largest angle. Okay. So again, I don't know why that's popping up. Come on, get off, get off, get off. And then make sure you're good here. Okay, so we've got perpendicular lines, give you congruent right angles. And then from that, we've got the exterior angle, which is 3, is more than 1 because an exterior is greater than any non-adjacent interior. Then 2 is more than 1 by substitution of the inequalities. And then in a triangle, the bigger side's opposite the biggest angle. All right, so you got, I think, 2 more proofs to try on your own for homework.